All right. Let's see. Oh yeah. Okay. Um, so why don't you guys pull out your normal tables? We'll start off with just a few normal distribution problems. All right. So let's see. All right, so those are your answer choices. This is our little picture. And we'll say diastolic, I don't know how to spell it, diastolic blood pressure. So, when you get your blood pressure, it's like two numbers, 120/80. Diastolic is the lower number, okay? It's like on your, the second heartbeat, okay. Diastolic blood pressure, we'll say, comes from a normal distribution with a mean of, what do I want to say, 73, and a standard deviation of 10. We'll say, what proportion of people have blood pressures lower than 80? Okay. You can go ahead and try that out. So your picture should have, we'll put 73 in the middle. How are we doing? It's fifth week Friday, so we're like halfway through the quarter. Some of you guys are like just a few weeks away from graduation. Yeah, so. Huh? You guys have jobs lined up? Interviewing, almost? Some of us. Working's just okay. But getting a paycheck is nice. All right. Okay, so just a few more seconds. I'm going to click stop here. So get your clicks in. 1, 2, 3, and stop. Okay, let's see what our answer is. You guys have picked C, and C is the correct answer. Okay. All right, and so, we're drawing a cutoff line at 80. And so we would turn 80 into a z-score. So the z-score for 80 is going to be 80 minus 73 divided by 10. We get a z-score of 0.7. We look up 0.7 and the column 0.00 in our z-table, and we get 0.7580. Okay, so our z-score is 0.7, but that's not the proportion of people who have blood pressures lower than 80. That answer is the area to the left of 0.7, and that's 0.7580. So this is our answer here. Yes, you can clap. And then, wait, that's not what I wanted to do. Hang on a second. I clicked the wrong button. Save as. Okay, if you picked 0.7257 because you decided to draw the cutoff line at 79, even though it says lower than 80, you might have chosen to draw a cutoff line at 79, and you got 0.7257. This brings up I guess, an important point, is that for the normal distribution, okay, the previous question was basically what's the probability that blood pressure is less than 80? Okay, this will have the same answer of less than or equal to 80. Okay? So because the normal distribution is continuous, between less than 80 and less than or equal to 80. Whereas with the with discrete distributions, there is a difference. Okay. Okay. Let's try another problem out. Do you need me to go back to the previous slide here? I don't know. Anybody still writing? We're okay? Okay. Okay. So let's change this. We'll say blood pressures come from a normal distribution centered at 73, standard deviation of 10, and we'll say, we ask, well, what proportion of people have blood pressures between 70 and 80? Okay. And so our answer, we're going to say, well, this is the thing that we want to get. We're going to say that, you know, the desired area that we want, this area, is equal to this area minus this area, okay? So we're going to find the area to the left, so we'll take the area to the left of 80, and we're going to subtract off the area to the left of 70. And we will be left with the area in between 70 and 80. Okay. So, okay, so let's put up some answer choices. So we want to get the area in between 70 and 80. What's up? All right, just a few more seconds, so get your clicks in. I'm gonna hit stop here. Okay. All right, let's see how we did. That looks pretty good. That is our correct answer. Okay, and so again, to solve this, we're gonna find the area to the left of 80. So we do, 80 minus 73 divided by 10, we get 0.7. This is the problem that we had on the previous page. And so we find the area to the left. Okay, area to the left of 70, z is equal to 70 minus 73 over 10. We get a z-score of negative 0.3. And then we get the area to the left is equal to 0.3821 when we look that up in the table. Okay? And so the area between 70 and 80 is going to be 0.7580 minus 0.3821. And when we do the math here, we get 59.3759. Okay, so this is 0.7580. This over here is 0.3821. And this is, okay, that's our answer here. So far, so good? Great. All right, let's continue on here. All right, so we'll say IQ scores come from a normal distribution with a mean of 100 and a standard deviation of 15. Okay, and we'll say what is the IQ of someone in the 90th percentile? Let's see. So the 90th percentile means 90% of people have scores lower than this. Oh, sorry. Let me fire up the the base station. All right, we'll say just a few more seconds. Okay, I'm going to hit stop. So if you haven't clicked your buttons, click your buttons right now. See how you guys did. Answer B is correct. Okay, and so the way our diagram looks is that we have colored in 90% over here. Okay. And we want to know what is the value that goes right here, okay? So we're first going to start by looking for, in our table, the value closest to 90%. And the value that we find closest is 0.8997, I believe. Okay? So we don't find 90% exactly, but we find something very close to that, and that's 0.8997. And that's in the row 1.2 in the column 0.08. So the z-score that corresponds to the 90th percentile is z is 1.28. Okay. This is, I guess, the hardest part of the problem, so I just want to make sure everyone's okay with this. Okay. So a few of you missed this problem, so we're trying to find the value closest to 90% in our table. And when we look, we don't see 90% exactly, but we see 0.8997. That's about as close as we can get. So that's z is 1.2, and the column is 0.08. So that's going to be 1.28. Z is 1.28. This tells us that the score is 1.28 standard deviations above the mean. Okay, and so our mean is 100, and each standard deviation is 15, and we are 1.28 standard deviations above the mean. So we're going to have, our score is going to be 100 plus 15 times 1.28. This is 100 plus 119.2. I'm sorry, not 119, plus 19.2, which gives me 119.2. Okay. Alternatively, I could have just used the z-score and said, well, z is equal to x minus mu over sigma. So that gives me 1.28 is equal to the x that I'm looking for, minus 100 divided by sigma of 15. Solving for x, we get 100 plus 15 times 1.28 is equal to x, which gives us the same thing, 119.2. Does this feel okay with you guys? Maybe just one more practice problem? Sure, maybe. Maybe you don't need it. Okay, yeah, thanks for the enthusiastic response there. And all right, so we'll say verbal SAT. Those scores, normal distribution, centered at 500 with a standard deviation of 100. I heard that they changed the SAT to go back down to just 2 subjects again, verbal and math. They got rid of the writing, or is that true, or is that not true? The writing is optional, which means it's required. Oh, I decided not to take writing because it was optional, right? It's like, oh, yeah. It doesn't look suspicious at all. Okay, so we'll say a university decides their cutoff to be the 25th percentile of scores. Okay, so we'll say, what is the minimum verbal SAT score needed? Okay. Okay, so Okay, are we ready? Looks like almost all you guys got this. Just click, 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 click. All right, and that is correct. So we want the 25th percentile. Okay, so we want this shaded area to be 0.25. Simple enough. Okay. So in our table, we're going to look for the area that's closest to 0.25. We don't find 0.25 exactly, but we find at negative 0.67, we find 0.2514. You know, we're faced between 0.2514 and 2.2483, and we're going to say 0.2514 is pretty close, and that's negative 0.6 and the column 0.07. So the z-score we use is negative 0.67. And so solving for x, we have minus 0.67 is equal to x minus the mean of 500 divided by our standard deviation of 100. And solving for x, we get x is equal to 433, just using algebra. And there we go. 25th percentile. Good enough? Okay, so that's normal model. Make sure we're going to encounter the normal model quite frequently in the future, so make sure you're comfortable with these types of problems, going from a score to a percentage or proportion area, or if I give you the percentile, going back to a score. Okay. Right now I'm going to introduce the binomial distribution. Okay. And so today I'm going to just talk about the binomial distribution as kind of a concept, and then on Monday we'll talk about calculating the probabilities for a binomial distribution. Okay. So this is still part of chapter 6. Okay. And here we're still talking about probability distributions. So with the binomial distribution, we repeat a random trial or a random experiment n times. Okay, so we do the same thing over and over again n times. Okay. Each trial has a probability p of a quote-unquote success. Okay. Success is an arbitrary label. We normally associate success with good things, but in these problems, it's just either the outcome happened or it didn't. Okay, and that outcome could actually be a bad thing. We could talk about, I don't know, something going wrong, but it's always just quote called a success. So each trial has a probability p of a success and a probability 1 minus p of a quote-unquote failure. Again, these are just arbitrary labels, not necessarily good or bad things. Okay. Okay. Each trial is independent of each other. And we are interested and the probability of x successes. Again, quote-unquote successes. Okay, so I'll list off some examples of things that are binomial distribution problems. For each of these problems, we have to be able to identify n, p, and x. Okay, and there could be multiple x, but we have to identify n, p, and x for each of these problems. Okay. Okay, so for example, I'm sorry, should I go back to the slide? Were you guys still writing? Yeah. Okay, now we're good? Okay, so example, I will flip a coin 4 times. Okay, and I want to know, if it's a fair coin, what is the probability that the coin lands heads 3 times? Okay, so in this scenario, n is the number of times we're repeating the random trial, so what is that? 4, we're flipping the coin 4 times. P is the probability of a success. So, well, first of all, let's label what a success is. So we'll say the quote-unquote success will be the coin lands heads. And so the probability of a success for each coin flip is what? 0.5. And the number of successes that we're interested in is 3. Okay? Simple enough. Okay, and this is a binomial problem with n 4, p 0.5, and x is 3. Okay? On Monday, we'll go through calculating these actual probabilities if we're given the n, p, and the x. But for now, we're just going to talk about identifying what a binomial problem is and identifying these quantities n, p, and x. Okay. All right, let's talk about, so in basketball, we'll say Steph Curry, he's probably a little bit better than this, but we'll say is a 90% free throw shooter. Okay, meaning every time he takes a free throw, there's a 90% chance that he makes it in. Okay, and this might not be true, but we will assume each shot is independent of the other. Okay. All right, so we'll say in a game, say he takes 9 free throws. What is the probability he makes at least 8 of them? Okay, Okay, so in this problem, let's identify our n, our p, and our x. So how many times are we repeating this random trial? 9, okay. And we'll say success will be making the shot. Okay. What is the probability of p then? 0.9. And what is my x? It's 8 or 9. Okay, because it says at least 9, our x is both 8 and 9. Okay, we want to know what is the probability of getting x equal to 8 or x equal to 9. Okay, and again, we'll learn how to calculate all of these values on Monday. Okay, all right, and you know the applications of this are endless. Well, not endless, but so let's say I've got a giant tub of M&Ms, okay? Okay, and so normally when you draw samples, or a sample out of a finite population, technically, like if I only had 10 pieces of candy and 3 of them were red and 7 were not red, if I draw a piece of candy and that one's red, then technically what's left will be 2 red pieces and 7 non-red pieces, right? And so the remaining probability is affected. But we're going to say this thing is so big that when I draw a piece of candy out and it's red or not red or whatever it is, the effect that it has is negligible. Okay, so we'll say it's so big that the effect of drawing a sample is negligible. Okay, and so we can say 15% of the candies in the bucket okay, so I'm going to say I draw a random sample of 50 candies. Okay, and I'm going to ask, what is the probability that I get at least 6 red pieces? Okay, so in this case, my answer is will be determined by n is equal to 50. My success will be is the piece red. And so the probability of a success will be 0.15, and x is equal to 6, 7, 8, at least 6 red pieces. So 6, 7, 8, all the way up to 48, 49, 50. Because technically, if I draw 50 pieces of candy, it is technically possible that by random chance, all 50 of them end up being red. It's incredibly unlikely for that to happen, but it is technically possible. If every time I draw, it's a random chance. Okay. So again, we'll learn how to calculate all of these things on Monday. But with that's it. Have a good weekend, you guys.